Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about circular motion, things going around in circles. It's an important special case because it turns out that there are lots of examples in the world where things, at least approximately, go around in circles. So let's dig in. And we'll start by considering a special case called uniform circular motion. And what do we mean by uniform circular motion? By definition, what that means is that the object travels at a constant speed, and we'll call the speed v, at a constant speed v, and we'll specify that the radius of our circle is lowercase r. And now I'm going to make a claim, which I will prove in a moment. And the claim is twofold. One is that such an object undergoing uniform circular motion undergoes an acceleration, which is, first of all, it's accelerating. That may be surprising to you, but the acceleration that it undergoes is directed towards the center of the circle, directed towards center of circle. And what do we mean by that? That means, for example, if the object as it travels around at any point as it's traveling around, if we're going to calculate the direction of the acceleration, it's going to be directed radially inward towards the center of the circle. And we refer to this as centripetal acceleration. Centripetal just means directed towards the center of the circle. So centripetal acceleration. And I'm going to make a second claim now. The second claim is that the magnitude of the acceleration, is, we'll call that magnitude A, it's equal to the speed squared divided by the radius of the circle. And to prove this, I'm going to take advantage of a figure that is in my version of the Wolfson textbook. And part A of the figure, so the object in this case is traveling clockwise around the circle. So at time one, the object is in position here. So it is, we're going to measure positions with respect to an origin at the center of the circle. So the vector R1 gives the position of the object at time t1, and a little while later, the object has moved into position 2 here, has position R2. It's rotated through an angle theta, and its position has changed. So if you look at part B of the figure here, delta R is the change in position, R2 minus R1, and we can see that delta R points in this direction, pretty much nearly tangent to the circle. Now, the velocity of an object as it travels along any path is always tangent to that path. So the velocity at time t1, which we'll call v1, points in this direction, tangent to the circular path, and hence perpendicular to the r1 vector. And similarly, at time t2, the velocity v2 is tangent to the path and hence perpendicular to r2. And because the object is not changing speed, we've specified uniform circular motion, by definition, constant speed. That means the lengths of these two vectors, v1 and v2, are the same. But nonetheless, the object is accelerating because the direction of the velocity vector is changing. So recall that the way that we define the average acceleration that occurs during some time interval delta t is just the ratio of the change in velocity vector divided by the duration of the time interval delta t. So the average acceleration vector, the direction of it will point in the same direction as this vector delta v. And if we look at the figure down here, we see that delta v points in the direction shown, which looks like it's directed towards the center of the circle. And if you really want to see that it's exactly towards the center of the circle, what you have to imagine is taking the limit that delta t gets smaller and smaller. And what you should be able to see is that as delta t gets smaller and smaller, v1 and v2 are going to become more and more parallel to one another because delta theta, the angle between them, is going to get smaller and smaller because we've waited less time. And as that happens, delta v becomes more and more perpendicular to each of these two vectors. And we know that the velocity vectors are perpendicular to the radial vectors. So we end up concluding that delta v points in the limit that delta t goes to 0, delta v is parallel to the radial vector and pointed directly radially inward towards the center of the circle. So we've argued this claim here. These figures verify our claim that the acceleration of an object undergoing uniform circular motion is directed radially inward towards the center of the circle. What about our second claim here, the magnitude of this acceleration? Well, to find a magnitude, we have to make an observation, which is stated here, which is that the two triangles that are drawn in this figure are similar triangles. And how do we know that? Well, similar triangles, uh, they have to have, the angles have all got to be the same. So if this angle is theta here, if the position vector has rotated through an angle theta, because the velocity vectors are always perpendicular to the position vectors, that must mean that v1 and v2 are differ by an angle theta, which is shown here. Okay, and these are both isosceles triangles because for a circular path, obviously the length of these position vectors is the same. It's just r. And this is an isosceles triangle because we specified that the speed of the object is not changing. So the lengths of these two velocity vectors are both the same. They're both the speed v, and therefore all three angles in these two triangles are the same. So they're similar triangles. Well, what does that tell us? Well, the fact that they're similar triangles means that we can write the following ratio. It's got to be true that the magnitude of the change in position vector, delta r, divided by r, is equal to the magnitude of delta v divided by v. Right? Because when you have similar triangles, the ratio of corresponding sides has got to be the same. So this left-hand side here corresponds to the ratio of this side of the triangle to this side, and the right-hand side corresponds to the ratio of this side of the similar triangle to this side. So this ratio, this equality follows from the fact that the two triangles are similar. And I can rewrite this using the convention that Wolfson uses, which is just save writing the absolute value signs. I'm going to rewrite this as delta r over r is equal to delta v over v, where it's understood throughout the Wolfson text that when we write a quantity without a vector symbol on it, we're just referring to the magnitude of that vector quantity. And now I can just rewrite this last relationship. I can write that delta v is equal to v over r times delta r, just rearranging. And then I can divide both sides of this equation by the time interval delta t. And now in the limit that delta t goes to 0, the left-hand side of this equation is just the magnitude of the acceleration. And then the right-hand side I can write as v over r times v, because in the limit that delta t goes to 0, delta r over delta t is just the speed v. So what we've proven after all this is that, as claimed, the magnitude of the acceleration of an object undergoing uniform circular motion is simply v squared over r. Okay, so let's just do a quick example. Let's try to get a feel for this. Take a realistic situation. Imagine you're coming off the Mass Pike and you're on one of these circular exit ramps where the exit speed is 40 miles an hour. And let's assume that the radius of the curve is 100 meters. You can approximate the circular path as part of a circle that has a radius of 100 meters. And if you look around a typical exit on the Mass Pike, these are sort of realistic numbers. Actually, the 40 miles an hour is a little bit high speed, but nonetheless, we're taking the curve a little fast. And if you're not, let's do all of this in SI units. So if you convert 40 miles an hour into SI units, you'll find that it's 18 meters per second. So what is the magnitude of the acceleration that such a car is undergoing? And also, let's try to get a sense for how to think about it. Is this a big number or a small number? What will you feel? How will it feel if you're riding in such a car? Well, this is just a simple plug-in. The acceleration of our car, we just said, is the speed squared over the radius of the circle. So the speed is 18 meters per second, quantity squared. The radius of our circle is 100 meters. The numerator works out to 320 units are meters squared per second squared, divided by 100 meters. So our acceleration is 3.2 meters per second squared. And if you want to get a sense for whether something is a big or a small number, you need to compare it to something. And one obvious sort of acceleration to compare it to is the familiar acceleration of a freely falling object. Remember, a freely falling object near the Earth's surface accelerates downward at g equals 9.8 meters per second squared. So in the current case, the acceleration of the car going around this circle has an acceleration with a magnitude which is about a third of g. And as we'll see when we talk about dynamics and how all the forces work, you'll end up seeing that you'll definitely feel this as you go around. If something is accelerating at a substantial fraction of g, you're going to sort of feel your body thrown in a certain direction as you go around. And I want you to think about a little bit about actually when you go around a curve, which way your body feels like it's moving. That's something that we will return to in a week or so. And now let's finish up by talking about a slightly more general case, the case of circular motion in which you're not traveling at a constant speed. We'll refer to that as non-uniform circular motion. And to talk about this once again, I'm going to take an example, a figure out of the Wolfson textbook, or at least my copy, my edition of the Wolfson textbook. And imagine that we've got the same car going around a circular exit on the Mass Pike, but now as you're going around the circle, you're appropriately stepping on the brakes a little bit so that you're slowing down, that your speed is decreasing. And now what can we say? Well, your acceleration still has a component which is directed radially inward, but now because the length of this velocity vector is changing over time, there's a tangential component to the acceleration as well. So because the object is slowing down, the tangential component, a sub t, is pointing in the direction opposite to the velocity vector. And if you want to know what direction your total acceleration is in, you've got to add these two components together. And if you add a vector pointing this way and one pointing this way, you get a vector qualitatively pointing this way. So what this figure really is showing is that as you move around a circular path or any curved path, there's going to be a component of your acceleration which is just associated with the fact that you're changing direction, and that's our radial or centripetal acceleration. And then you can also, in general, have components of the acceleration that are associated with changes in speed, and those are going to be directed either anti-parallel or parallel to the velocity vector, depending upon whether you're slowing down, as in this case, or speeding up. So to make this a little bit more concrete, let's consider a specific example, which we'll call stepping on the gas. Imagine you've got some sort of curved roadway that follows this contour here. And imagine that as you're traveling along the curved pathway, you're actually not braking, you're stepping on the gas. So your speed is increasing. And the question is, what can you say about the direction of the acceleration that you're undergoing at each of these 3 points, A, B, and C? Well, at point A, there are going to be two components to your acceleration. There's going to be your radially directed inward component A sub r. And now, because you're speeding up, the tangential acceleration component is going to be directed the way I've shown here. So when you add AT and AR, you're going to get a total acceleration at this point that points roughly this way. Okay, what about at point B? Well, at point B, the roadway is not curved, so there's going to be no radial component to your acceleration. There's just going to be a tangential component, and that tangential component is going to point along the path. So A at this point is just exclusively due to the tangential component of the acceleration. And finally, at point C, we've still got our tangential component, and now the tangential component is going to point in this direction. Because of the curvature of the path, the radial component is going to point radially inward. So A sub r points radially inward this way. And when you add A sub r and A sub t, you get a total acceleration which points roughly that way. Okay, so you drive carefully out there. Don't step on the gas too much. And that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye-bye.